Good afternoon, student. Welcome to today's physics class. I am excited to dive into a crucial topic in the world of fluids, that is pressure, which is belongs to 11th physics. Yeah. Okay. So today we will focus on three main objectives. First, pressure, then Pascal law, and finally pressure variation with depth. Okay, clear? Pressure variation with depth. Okay. So understanding the concept of pressure in fluids, which is very important to understand the many more real life applications. Yeah. And already you know that some of the important terms related to the Pascal law. Yeah. So Pascal law and its incredible applications, and finally deriving and using the formula for pressure variation with depth. By the end of this session, you will be able to explain how a massive hydraulic lift works and why deep sea divers need special chutes. Okay. Okay. Let's kick off with a quick thought experiment, a motivational story called The Nail and the Bed of Nails. Okay. So imagine I ask you to lie down on a single sharp nail like that. Yeah. So I ask you to lie down on a single sharp nail that would cut instantly, right? Now imagine lying down on a bed of hundreds of nails like that. Yeah, like that. Surprisingly, you could do that without getting cut. Why? The total force is same in both cases. That is, total force means your weight. Yeah. But on a single nail, all that force is concentrated over a tiny area like that. Okay. Tiny area. So total force is same in both cases. That is your weight. But on a single nail, all that force is concentrated over a tiny area. So that wood pressure is high. So here pressure high. Yeah. Large force, but tiny area. So pressure is huge. Okay. On the bed of nails, the force is distributed over a large area. Large area means many nail tips, because here you can see the single nail, here you can see the hundred of nails. So the larger area, yeah. So here large area, but same force, yeah, same force. So the pressure on any single point become small. Here pressure on any single point becomes small, enough to be harmless. Yeah. This simple idea how force and area interact to create pressure is the core of what we will study today. Okay, right? So Let's now recall some prior knowledge with a quick 3-question MCQ quiz. I am sharing the screen now. Yes. Yes. Okay. Good. So first question, which quantity is classified as a scalar? Option A, force. B, area. Option C, velocity. Option D, acceleration. So which one is scalar quantity? Which one is scalar quantity? Option A, option B, option C, option D. Which one is? Which quantity is classified as a scalar? Already you know that acceleration is a vector quantity. Yes, good. Velocity also vector quantity. Yes. Force is a vector quantity. Yes. So area is a scalar quantity. Good. Yes. Area. Very good. CJG. Blingenham town. Very good. Second question. What is a term for the force exerted by the object on the surface directly beneath it due to gravity? So, what is the term? What is the name of the term? The force exerted by an object on the surface directly beneath it due to gravity. Momentum, weight, thrust, impulse. Which one is correct? Yes, the same center. GJC Willingham Town. Yes, good. Weight. Yes, very good. So weight means force exerted by the gravity on the surface of the object. Yeah, very good. Okay, right. Then next, last one, density. You know that rho, yeah, is defined as, what is the formula or what is the definition for density? Option A, mass per unit volume. Option B, force per unit area. Option C, area per unit force. Option D, force per unit volume. Which one is correct? Yes, same center. Very good. Any other students? Any other centers? Any other students? The response coming from same CJG Lingaram town. Any other students? Any other responses from you? Okay, okay, okay. So density is defined as very good. Mass per unit volume, M by V, which gives density. Okay, let me check the answer. Yes. Which quantity scale is classified as a scalar? Yes. Option A. Okay, good. Okay. So which quantity scalar? Area and due to gravity, force exerted on the object due to gravity is called as weight. And finally, density is a mass per unit volume. Good. Okay. Super. So now let's establish the fundamental concept using the whiteboard. Okay. So first, pressure in fluids. Pressure in fluids. Pressure, simply put, is the normal force, normal force exerted by a fluid per unit area. This is a simple definition for pressure. Normal force exerted by the fluid per unit area. Okay. So we define it as pressure P equal to force by area, F by A. Okay, F by A. This is a pressure. It is crucial to remember that unlike solids, fluids, unlike solids, fluids exert pressure in all direction. Okay, in all direction. Unlike solids, fluids exert pressure in all direction, up, down, sideways. Okay, in all direction. This is why you feel pressure on over your body when you dive underwater. Yeah. So this is the reason behind that you feel pressure all over your body when you dive underwater because of pressure due to that fluid, that water. Okay. So this is all belongs to pressure in fluids. Second, Pascal law. So this is a powerhouse principle. Pascal law is a powerhouse principle. So it states that pressure applied pressure applied to an enclosed incompressible incompressible fluid is is transmitted undiminished undiminished to every portion of the fluid. Okay, and as well as and the walls of the container, walls of the container. Okay, so this is a Pascal law. So that law state that pressure applied to an enclosed incompressible fluid is transmitted undiminished. Undiminished means that magnitude does not reduce. Okay, so the pressure transmitted undiminished to every portion of a fluid and the walls of the container. In simple terms, suppose if you push on a bottle of water, okay? Suppose if you push on a bottle of water, that push, that pressure is felt equally everywhere in the water, okay? Suppose if you push on a bottle of water, that push already you know that push is called as is known as pressure. Yeah, that push is felt equally everywhere in the water. This equality of pressure is a secret begin massive mechanical advantage. Okay, okay, right. And the third one, the variation of pressure with depth. The variation of pressure with depth. Pressure with depth. As we discussed in the bed of nail story, pressure depends on the weight of what's above it. Yeah, pressure depends on the weight of what's above it. So in a fluid, the pressure at a depth. So for example, we can say that H. So the pressure at a depth H is the sum of the atmospheric pressure PA. So pressure at H. So pressure at depth. Okay. So sum of the atmospheric pressure and the pressure due to the weight of the fluid column. Weight of the fluid column means already you know that rho g h. Yeah. So P is equal to PA plus rho g h. So this P means the pressure at the some depth h. So 1 meter, 2 meter, like that. So this is a constant value. Yeah, atmospheric pressure. So this is the rho g h. So rho means density of the fluid. You can change the fluid, water, honey, like the gasoline, like that. Okay. G means acceleration due to gravity. You can change that Earth, Moon, Mars, like that. Okay. And the final one, H means height of the fluid column. Yeah, height of the depth. Okay. So here, very important term is the pressure increases linearly with depth. Okay. So pressure increases linearly with depth. Okay. Because rho means density of the liquid. That is constant for that case. G constant for that case. But you can change that height. So that is depth. Yeah. So pressure increases linearly with the depth. Clear? Okay. Right. So let's see this concept in action. I am opening FET simulation now. I will share the screen now. Yeah. Okay. So we are going to see the physics of fluids using this FET simulation. The name is under pressure simulation. Okay. So our goal is to understand what pressure is, especially when you are submerged in a fluid like water, and to explore Pascal law. Okay. Okay. Now look at the screen. We have a large container. You can see that. Yeah. So we can fill that with the water like that. Okay. So we have a large container filled with the water. Here you can see the one device. It is a pressure gauge. Okay. So this device allows us to measure the pressure at any point in the fluid and as well as in the atmosphere. So here, this is a pressure value at the atmosphere. That is 101 kilo Pascal. Okay. Okay. Right. So now I'm going to place a gauge right at the surface of water. I will take the another gauge and put it on the surface of water like that. Okay, you can see, you can move like that. Okay. So here you can see that the pressure value 101.663 kilopascal, which is slightly higher than the previous value. That is above value because that pressure, this pressure is atmospheric pressure. Yeah. Okay. Look at the reading on the gauge. Even at the surface, there is a pressure reading. That is a pressure from the atmosphere pushing down on the water. Okay, clear? Now, watch carefully as I slowly slowly move the pressure gauge deeper into the water. What do you observe happening to the reading? Yes, it increases. Exactly. Okay. The pressure increases the deeper we go. Why do you think this is Why do you think this is? Think about what is pressing down on the gauge. The deeper the gauge goes, the more water is stacked up above it. Yeah, like that. Yeah, above it. The vertical column of water has weight, and the weight pressing down is the pressure we measure. So this phenomenon is called hydrostatic pressure. It increases directly with depth. Okay. Okay. Now, now I will place the one gauge here like that. Okay. I am going to move the other gauge same height like that. Okay. You can see like, yeah. So now watch this. I am going to keep the gauge at the same depth. You can say 3 meter, 2 meter, 1 meter like that. But to move to the side of the container. Does the pressure change? Does the pressure change? No. Yeah. Yes. Correct. No. This shows us a key fact. Pressure in a static fluid depends only on the depth, not the horizontal location. Okay. Not the horizontal location. And you can change the shape of the container. Here also, you can see that same concept. So here you can see the 1 meter. Yeah. So now pressure 111.350 kilopascal. Now I am moving another gauge like that. Yes. So the shape of the container changed, but the pressure same. Okay. So the pressure in a static fluid depends only on the depth, not the horizontal location or the shape of the container. Okay. Clear? Right. So now I'm going to use the controls on the simulation to change the fluid. Here you can see that water. Okay. Instead of water, let's switch into the honey. And please see that pressure gauge reading. Color also changing. Denotes a honey. Like that. Look at the pressure reading now. Has the depth changed? No. But the pressure is significantly higher. Yeah. Why is a fluid denser than water, like honey, exerting more pressure at the same depth? It is because of its density. Okay, density. Honey has more mass packed into the same volume than water. Okay, honey has more mass packed into the same volume than water. A column of honey weighs more than equally tall column of water. Therefore, the weight of the fluid pressing down is greater and the pressure is higher for the honey compared to the water. Okay. So this confirms the full relationship for hydrostatic pressure. So it depends on three things: the density, rho of the fluid, and the depth. And again, you can change the acceleration due to gravity. So here, gravity. So 9.8. Now I will change that gravity to the Jupiter. And please also watch that reading on the gauge. Yes, huge, significantly increasing. Yeah. So this is a relationship for hydrostatic pressure. So it depends on the three things: density, acceleration due to gravity, depth. That's why P is equal to rho g h. P is equal to rho g h. Clear? Okay. So now I will share another one device, that is hydrostatic hydraulic lift. Sorry, hydraulic lift. Yes. Okay. So we learned about Pascal law. So which is that any change in pressure applied to a confined fluid is transmitted equally throughout the entire fluid. Yeah. Okay. So we are going to see this powerful law in action with the GeoGebra simulation, which models a hydraulic lift. Okay. Right. Take a moment to look at the setup. A hydraulic lift is essentially a two fluid filled cylinders. Okay. Two fluid filled cylinders connected by a pipe. Here you can see that connected by a pipe. So we have a small piston on the left. Yeah. Small piston on the left, where we apply an input force, that is F1, over this small area. Over this small area. So here you can see that radius, diameter as well as. Okay. So if we increases the area by increasing the diameter, okay, here you can see that P1 is equal to F1 by A1. That is A1 means area of that small piston. Clear? Okay. So where we apply an input force F1, okay, and the large piston on the right, which generates a large output force, that is F2, which generates a large output force F2 over the large surface area, large area A2. This is how mechanics, car repair, and construction equipment works. Okay, right. So if I apply the force here, you can see that yes. So I am applied force on the small piston. So F1 by A1 gives pressure, that is 15.92 Pascal. So that pressure transmitted equally throughout the liquid, and here force by area. So force 5,000 Newton. This is okay. This is the weight of the car. So force is 5,000 Newton, and area of this large piston. So here also you can see that pressure is 15.92 Pascal. Same pressure. Yeah, you can see that same pressure. The pressure equally transmitted over the fluid, confined fluid. This is a hydraulic lift. This device is based on the Pascal law. Clear? Okay, good. So, very important formula is P is equal to F by A. So, suppose we have a hydraulic lift. The basis of this device is Pascal law. The fluid is rest and enclosed. The pressure on the input piston, that is called as P1, must equal to the pressure on the output piston, P2. So this is F1 by A1. This is F2 by A2. Yeah. So this allows a small force applied over a small area, that is A1, to generate much larger force, F2, over a large area. Clear? Okay. Now, another one important term, that is mechanical advantage. That is So this is also called as mechanical advantage. You can write it like that also. Okay, A2 by A1, large area by small area, act as a mechanical advantage. This is how devices like car hydraulic lifts and hydraulic brakes works. Clear? Okay. So now we have seen the theory. Let's apply it by solving two numerical problems. I will share the screen. So this is the first sum, problem number 1. Application of Pascal law, hydraulic lift. A hydraulic lift is designed to lift cars with a maximum mass of 3000 kg. If the area of the input piston is 10 centimeters square and the area of the output piston is 1000 centimeters square, okay, what is the minimum force that must be applied to the input piston to lift the car? Take G is equal to 10 meter per second square. So here you have car with maximum mass 3000 kg. Okay. Input piston area 10 centimeter square. Output piston area 1000 centimeter square. Very good. And then you have to find the minimum force, that is F1. You have to find the F1. Okay. So minimum force that must be applied to the input piston to lift the car. Okay. Right. So please remember that. What is the formula? What is the formula? So here mass of the car. So we can say that mc. Okay. 3000 kg. Okay. And area of the first piston, input piston, that is 10 centimeter square, and the area of the output piston, that is 1000 centimeter square. Okay. G is equal to 10 meter per second square. Okay. Right. So we have to calculate the first of all output force, F2. The force needed to lift the car is equal to the car's weight. Yeah. The force needed to lift the car is equal to the car's weight. That is F2 is equal to, already we know that force is M into G. M into G. Mass of the car 3000 kg and G 10 meter per second square. So we will get 30,000 Newton. Yeah. Kilogram meter per second square means Newton. So 30,000 Newton. This is a F2. Now apply the Pascal law. That is F1 by A1 is equal to F2 by A2. F1, we got to find the F1. So F1 equal to A1 into F2 by A2. A1 into F2 by A2. Okay, right. So F1 is equal to F1 is equal to A1 F2 by A2. Now substitute the values here. F1, A1 10 centimeter square, A2 1000 centimeter square, F2 30,000 Newton. Okay, right. Centimeter square, you can cancel it out. 10 0 0. Okay, clear. So F1 gives 300 Newton. So this is a minimum force. This minimum force that must be applied to the input piston. Okay, this minimum force 300 Newton must be applied to the input piston. Notice we did not need to convert the areas to meter square because the units of area cancel out in the ratio. Okay, So we did not need to convert the areas to meter because the units of area cancel out in the ratio. Okay. Now we will move into the second problem. I will share the screen. Share the screen. Okay, nice. Yes. Problem number 2. Okay. The variation of pressure with depth. What is the absolute pressure at the depth of 50 meter below the surface of the sea? Density of sea water, rho 1030. Okay, 1030 kilogram per meter cube. Atmospheric pressure PA. Already I told you that is atmosphere is constant. That's 101 kilopascal. So here 1.01 into 10 power 5 Pascal. G 9.8 meter per second square. So what is the absolute pressure at a depth of 50 meter below the surface of the sea? Clear? Okay. So we have depth, that is height. For the second problem, we have depth, h, 50 meter. Density, density of the sea water, rho. And atmospheric pressure, PA, 101. Okay, 1.01 in 10 power 5 Pascal. And G, 9.8 meter per second square. Okay, clear. Okay. So we have to apply the, we have to find the absolute pressure. So what is the formula? Already we know that P is equal to PA plus rho GH. You know that. Yeah. P is equal to PA plus rho GH. So rho GH, rho GH, we have to multiply that. Right? So G 9.8 meter per second square. And finally, height, that is depth, 50 meter. Clear? Okay. So we will get the 504, 700 Pascal. You can multiply that 504, 700 Pascal. This is a rho G H. So we got to find the P. Clear? Okay. 101 into 10 power 5 Pascal. This is the value of PA. And plus we have to put here. Okay, right. So for this, we have to convert into 1.01 10 power 5 into 101, 00 Pascal. Okay, to add to this value. Okay, right. So you will get the 605, 700 Pascal. Clear? So approximately 6.06 into 10 power 5 Pascal. 10 power 5 Pascal. This is the value of the absolute pressure. 605 700 Pascal, approximately 6.06 into 10 power 5 Pascal. Clear? Okay. So the absolute pressure at a depth of 50 meter is approximately 6.06 into 10 power 5 Pascal. That is about 6 times the atmospheric pressure. Yeah. Already you know that atmosphere 1.01. But here you can see that 6.06. So that about 6 times the atmospheric pressure. This is why deep sea divers need those specialized suits to protect them because the pressure is huge. This is why deep sea divers need those specialized suits to protect them. Okay, right. So now it's time for a quick quiz. Okay, I'm sharing the screen again. Okay, right. So first question, the SI unit of pressure. What is a SI unit of pressure? What is a SI unit of pressure? Yes, very good. Yes, good. AGBP, ABRG. Yes, yes, very good. What is a SI unit of pressure? Very good. Pascal. Okay, good. Then next is second one. Which law governs the working of a hydraulic lift? Which law governs the hydraulic lift? Yes, good. APRJG. One of us C. Correct. Very good. Yes, Willingham. APMS. Yes, APMS. Very good. Yes. Which law governs the working of a hydraulic lift? Yes, very good. Good. Pascal law. So hydraulic lift is the device, okay, which is working based on the principle of Pascal law. Good. Third one. If the area of a force application is doubled, if the area of a force application is doubled, the pressure exerted, that is, you can keep the force constant, okay? The pressure exerted will double, remains the same, half, quarter. Which one is correct? Good. Again, good. Very good. Good. KGBB Anandapuram. Correct. APRJ. Correct. Yes. Any other students? Any other students? Very good. Yes. Half. Willingham. MSM. GJC girls. Very good. Yes. Yes. So the area of the force doubled. Pressure half. Yes. Good. Yeah. Very good. Yes. Option C is the answer. Okay. Because pressure P is equal to F by A. Already you know that. Okay. Right. Now we will move into the fourth one. How does a sharp knife cut materials more easily than a blunt knife? How does a sharp knife cut materials more easily than the blunt knife? Option A, it applies a greater force. Option B, it has a larger surface area. Option C, it concentrates the force over a small area. Option D, it reduces the applied force. Which one is correct? Very important question one. Yes, option C, option C. Yes, government junior college, very good. AP, RMG, okay, Willingham. Yes, Krishnaveni, KGBP, APMS, very good. Yes, option C, correct, very good. It concentrated the force over a small area. Yeah, so very good, good. And the final one, according to Pascal's law, when pressure is applied to the confined fluid, it is transmitted to option A, only to the bottom of the container. Option B, in proportion to the volume of the container. Option C, undiminished to every point in the fluid and the walls of the container. Option D, only in the direction of gravity. According to Pascal law, when pressure is applied to confined fluid, it is transmitted to, yes, correct. APMS, Government Junior College, also KGBB Anandapuram, yes, good, yes. MSM, GJC Girls, Willingham, yes, good. Extra many GJC Girls, very good. Okay, right. So here also the Pascal law. So the pressure applied to the confined fluid, which is transferred to undiminished every point in the fluid. Yes, KGBB. Yes, correct. Every point in the fluid and the walls of the container. Okay, let me check the answer. SI unit of pressure, you know that, Pascal. Which law governs the working of hydraulic lift? Pascal law. If the area of the force is area doubled, pressure half. Yeah, half. And the final one, how does a soft knife cut materials more easily than the blunt knife? Yeah. So it concentrates force over a small area. Okay. For the final one, I did not select, but the option is C. Okay. C is the correct answer. Okay. Undiminished to every point in the fluid. So I forgot to click the option C. Okay. According to Pascal law, when pressure is applied to the confined fluid, it is transmitted to option C. Is the correct answer. Good. Very good. So now is the time for your doubts. Okay. So any questions? If you have any question, please ask me. You can unmute or use the chat. Can someone explain in your own words why the pressure is the same at all points at the same horizontal level in your liquid at rest? This is also known as a hydrostatic paradox. Why the pressure is same at all points at the same horizontal level in a liquid at a rest. Okay. Okay. Right. So to wrap up, let's quickly review the core concepts. First of all, pressure is equal to force by area. Yes, the force is perpendicular to the area. Okay, force is perpendicular to the area. So P is equal to F by A. SI unit is a Pascal or Newton per meter square. Then next one, Pascal law. Pressure applied to the enclosed fluid transferred equally throughout. This allows a small force generate a large one, forming the basics of hydraulics. That is F1 by A1 is equal to F2 by A2. And the final, pressure with the depth. Pressure increases linearly with the depth due to the fluid's weight. The absolute pressure is given by P is equal to PA plus rho GH. Okay. Okay. Finally, for your homework, I will share the screen. So please complete the following two problems, which challenge your conceptual and numerical understanding. Please note it down. I'm sharing the screen. This is your homework. This is your homework. Yes. Please note it down. First one, homework conceptual question. Okay. A beaker is completely filled with water and its top is shielded with a light plate. If the beaker is inverted, the water does not float. Explain this phenomenon using the concept of atmospheric pressure and the pressure variation with depth. A beaker is completely filled with water. Its top is shielded with a light plate. If the beaker is inverted, the water does not float. Explain this phenomenon using the concept of atmospheric pressure and the pressure variation with depth. This is the first one. Second one, numerical problem. First one is conceptual question. Second one is numerical problem. A diving well is lowered into the ocean. At what depth will the pressure be? Exactly three times the atmospheric pressure. That is 3 into PA. So 3 times the atmospheric pressure. A diving well is lowered into the ocean. At what depth will the pressure be? Exactly 3 times the atmospheric pressure. 3 PA. So you can take that PA. So which is 10 power 5. Okay. Approximately PA is approximately 10 power 5 Pascal. And rho GH, rho seawater, density of seawater, approximately 1000 kilogram per meter cube. And the final one, G, you can take it as like 10 meter per second square. Okay. This is all for today. Thank you, students. Thank you, teachers. Jai Bharat, Jai Hind, Jai Vidyas. Thank you. Thank you all. Karthik sir, I got answer.
Okay, sir. Shall I wind up the session now?
Yes, sir. Yes, sir.
Yeah. Thank you.
Thanks. Thanks.
Thank you.